right. I understand this is the first talk in the morning, so I'll do the best I can to make it a little interesting, at the same time light enough. And maybe instead of it like being just me speaking, I'll try to maybe be a little bit more collaborative with you, and then maybe you can help me out. If I say something absolutely stupid, please correct me. I do that sometimes. And also, I did speak at conferences before, but generally, they've been more like security conferences. I think this is the first time I get too involved in a conference that's more development heavy. And based on the discussions I've had with some of the folks yesterday, like a lot of smart people around here, so I really like this opportunity to basically learn from others. Okay, so I can start. And first of all, my name is Yousif Hussin. I'm a security engineer at Google. I'm part of a team called the Enterprise Infrastructure Protection Team. But the talk that I'm going to do now is going to be related to a team that I left recently. It's a previous role. The team I'm part of right now is Enterprise Infrastructure Protection Team. Is the team that's responsible for building security controls for Google's infrastructure. And there is a bit of focus on securing the use of clouds by Google. So when Google uses clouds, and that includes like not just Google Cloud, Azure, and AWS. So we're the team that's responsible for making sure it's done in a safe manner, and the infrastructure is pretty much secure. So we want to enforce all the security policies so that it's secure by default. Now, in my previous role, I was in a team called the Vulnerability Coordination Center. And this is a fairly new team at Google, and based on my experience, it's generally in the industry. It's a bit of a new thing. So I understand that there's vulnerability management, and pretty much all companies, all large companies have like a team or an individual that does vulnerability management. But what we do here is a little bit different. What we do here is there's a team that specializes in addressing critical vulnerabilities. And what that means is sometimes you have a vulnerability that is so critical, and fixing it and remediating it across a company like Google is a lot of work. And it gets really stressful. It gets so difficult on a technical side, but also on the non-technical side, and you want somebody who knows how to manage this, orchestrate it end to end. And this is basically what the Vulnerability Coordination Center team does. It's one of the core roles. I think it's the most important part of the role. I was part of that team, and there was a time I was leading an engagement or a response to a vulnerability myself, and this is the one I'm actually going to go through during this talk. The other thing I want to mention, I'm also part of the team that manages the bug bounty program for Google. So when you submit a report, like find a vulnerability to Google, I would triage it, reproduce it, and then work with the developers on how to fix it. Another part of my role that I really enjoy is development of security tooling. You could say I'm a security engineer / software developer or software engineer, because I do a lot of development of tools for Google. And because we do it for Google, we have to do it at scale. So I have to think like a software engineer. And that's really different from like a security engineer who's just writing scripts to do security stuff. An example of that, I did develop an automation for Google that basically ingest public information about vulnerabilities that are known to in the wild or are outside of Google and people know about it, and then automatically correlate that data with intelligence data that correspond to that vulnerability. And if there is an exploit that's found in the wild, or if it was identified that this particular vulnerability could be exploited over the network, over the internet, things like that, my automation would automatically adjust the ticket for that particular vulnerability and get it to the developer so that they can fix it. And then the priority can adjust up and down based on the severity of that vulnerability. So that's one of the things that I worked on myself and I led the development of. One thing that is interesting between these two teams is the bug bounty and VulnCC. This one is internally is called Whoops, but they just say it's VRP publicly, VRP. VulnCC is that VRP team would triage all kinds of vulnerabilities. And not all vulnerabilities need to be handled by VulnCC. It's only the very interesting, complex stuff that gets escalated from here to there. And I'm part of two teams. I'm actually the only one that is part of both. So sometimes I would be sitting here And then I would triage the vulnerability and be like, oh, this is complex. We really need some help over there. And then I would escalate it there, and I would do I would do that work over there. And I did really enjoy this kind of work. I like vulnerabilities, working with vulnerabilities, identifying them, exploiting them. Just finding ways to break stuff is something that I enjoy doing. So, Vulnerability Coordination Center, I think I already talked about this. So, how do we do remediation at scale at Google? So, the Vulnerability Coordination Center is a team that knows the technical side of things. How do you fix this technically? How do you fix things technically? How do vulnerabilities get identified and fixed and reproduced? But also at the same time, how do we manage an incident at large scale? Traditionally, a lot of companies, you would have a team that does things like, yeah, we got hacked. We want to do management for this incident. We want to analyze the malware. You know, like we got a phishing email or whatever. All that's kind of traditional stuff. And then we have a team that does incident management for that. Now at Google, we do something a little bit more interesting. For vulnerabilities, if a vulnerability is identified and it's critical, even before you get hacked, we already declare this an incident, and we manage it like an incident. We already have a problem. There is a vulnerability. Somebody might find it, and somebody might exploit it. Somebody might hack us. And as you probably agree, it is a big deal. Like just a funny example, like if there's a vulnerability and somebody found out how to shut down Google search, for example. This would be something that would go to the Vulnerability Coordination Center to lead. And time is really important in things like that. So I wanted to build a little bit of context, just so we're all on the same page. And I don't think a lot of this is going to be foreign topics to you, but let's just make sure that we're all on track. First of all, how many of you can actually look at bits like this and tell what this is, just by looking at bits? Like, can you look at this and say, oh, this is a Hello World program? Really? Nobody can? OK. Yeah, so as you probably know, you would write code in C or wherever, you compile the program, and then it goes all the way down to a set of bits that represent instructions for the machine to perform, right? And then, as you know, there's a disassembler that you could use. Basically, can actually take a step back into assembly, right? And then that's kind of like, not everybody can read it, but it is probably the closest to the machine that a human can read. So the first time I was having a conversation with someone, and then I was like, well, looking at bits, that's difficult and stuff. And then they were like, well, there's a disassembler you can use. You can actually get to this. And I was like, wow. Nice. But that didn't help. I mean, how many of you read assembly day to day? Oh, nice. It's pretty impressive. OK. So I do a little bit of this in the security realm, because before I used to do some reverse engineering for malware. And when you do reverse engineering for malware, a lot of times you stumble upon assembly a little bit. But one of the things I did when I was working at a bank called JP Morgan Chase a few years back is building a system that would automate the analysis of malware so that the security engineers wouldn't have to read assembly code. So it makes it easy. But anyway, so this is an instruction in assembly. And this one is pretty easy. It's move EAX, EBX. It's kind of like it kind of tells you that you're moving something from a place to another. And in the machine, there's like these boxes. They're called registers, right? And at the end of the day, what the computer does is moving bits around between these registers. And then it would do some computation on them. So in the case of move, EAX, EBX, the move is the instruction itself, but then you've got the operands, which are the source and the destination. And in this case, you're moving something from a register called EBX to a register called EAX. OK, so that's simple. But then you've got an instruction that looks a little bit like this. Move SB. So this one doesn't have operands, but it is a move instruction. You're still moving something from a source to a destination. The only difference in this is that the operands are implicit. So just by using this instruction, the machine already knows moving from where to where. And then before it, you've got rep, which is basically just repeating the instruction. And this is the setup for the origin destination that I told you about, the machine would do behind the scenes. Okay. So this rep that basically tells the machine, hey, repeat this instruction, is called a prefix. If you do it like this, the machine instruction would work just as expected. But what would happen if you give a machine instruction that looks like this, rep, rep? Would it break the machine? Would it cause an error? Does anybody have any idea? Hmm? It's kind of, so it wouldn't do anything. It would ignore it. Like even if you do something like this. It would be like, okay, that's fine. I don't care. I'm just going to take the one rep. I'm just going to use that. So when we're talking about registers, you've got the operand, and the operand here, EBX, for example, this represents a register. And this is 3 bits, which basically means how many registers we could have in a system of 32-bit. Like 8, because with 3-bit, you can address 8 registers, right? But when in 64-bit systems, how do we address it with 3 bits? So turns out what happens is that when they designed it, they were like, well, remember this prefix that we could ignore? How about we don't ignore it? We could actually just borrow a bit from it. Now we have 4 bits, and now we can address 16 registers in a 64-bit system. So the 64-bit system is kind of like a hack in this case. It's not really 64-bit, but anyway. Now, another concept I want to cover quickly, just to make sure that we're all on the same track, is this. ERMS, FSRM, I think when I came across like terminologies for different things and technologies, these are probably among the top, ugliest names I've ever come across, and I always forget what they stand for. But I'm going to try. ARMS, I think it's extended, enhanced, repeat, move, store. And FSRM is fast, short, repeat, move. What these features are features that are introduced in Intel CPUs. And what they do is they're basically a performance feature. Start with ERMS. It's basically a performance feature that basically makes some of the repeat move operations a little bit more efficient in the system. The only issue with it is that when the operation involves a block of something like something small, a little bit less than 256 bits, then it wouldn't be worth the investment of using it because it has like some cycles of overhead, have to do a few things before actually running the operation. And that's what FSRM is for. It would give you that benefit of the performance feature in small blocks, for small blocks. The last concept I want to cover before I go to the response story is this. Does anybody know what this logo is? So let me tell you something. This logo, everybody in the room knows what it is, but at the same time, everybody in the room doesn't know what it is. You're going to know what I mean by that later, but I'm going to get back to this. It's important. So a response story. So what happens is, at Google, we have security researchers. What they do all day is trying to identify interesting vulnerabilities. And sometimes they identify vulnerabilities in CPUs. So one of the things that they do is they would get one program, and they make another copy of it, and then with slight different characteristics in it, you would expect the program would produce the same output. But if you have these different characteristics and it produces a different output, then you would assume something is wrong here. So what they would do is they would basically get these 2 programs and run it. And turns out when they were doing this, like testing the 2 programs with different characteristics, any system that has the feature of FSRM, and it uses the this prefix that gets borrowed for 16-bit, for 64-bit systems to address the 16 registers. And there are certain conditions would basically cause a denial of service. Not denial of service, let's just say it would cause a machine check exception. Okay, so machine would basically just halt. That's it. So that's what they found. And they were like, okay, well, that's interesting. The machine gets shut down. And that basically was the foundation of a vulnerability that was identified, called Reptar, affecting Intel CPUs. But it doesn't really sound like a problem, right? Like, what does it mean? Like, you run some code in your system and it shut down. Like, it's not really a big problem, right? Is it? It wouldn't be a concern, would it? Yeah, okay. So you got a piece of code, you run it on your system, and your system runs an Intel CPU that's vulnerable to this, and it will shut down. Why is that a problem?
Would be cool to shut down a data center that way.
But it's your own data center, right? It's your own data center, you have access to it, and you basically put the code, and then you run it, and you shut down systems, right? Yeah, that's basically what I was looking for, the cloud. Because it turns out that when you run this on a guest machine on a cloud, it would actually cause a machine check exception on the host machine, not just the guest. So if you think cloud, this is kind of a disaster, right? Like because the cloud is basically based on the idea that you're basically sharing in machines, right? So you just spin up a virtual machine on Google Cloud, and you shut down the physical machine. Like, it's not fun, right? I mean, if you're the attacker, it could be fun, but for us, no. So I'm going to go through some certain stages on how we actually responded to this particular vulnerability. So this is what happened. We know about Reptar internally at Google, and now we're going to have to respond to this. We're going to have to find out if we're vulnerable to it, how are we going to fix it, and all that kind of stuff. And this is the part that I led at Google, and it involves certain stages. And it starts from, this is just a way to illustrate it. I find it really easy. Basically, we're going to go from here all the way down to the end, and start with something called an impact assessment. Yeah, that's easy, but the way that we do this is that at Google, we have to answer certain questions like, okay, this is a vulnerability. How could you exploit it? Is it easy to exploit? Do we have a product that uses a system that's vulnerable? And then we come up with like an impact. And like I said, in this particular case, is it really concerning? We kind of are in agreement that for cloud, it is concerning because you can basically shut down a machine that hosts multiple guests. This is basically the guy that said it's not a big deal. But I guess we are in agreement that it is kind of a big deal in cloud. So what would be the first product that would come to mind when we're talking about cloud that could be vulnerable to this?
Virtual private servers.
Yeah. Or Google Cloud in general.
Yeah.
Okay, so Google Cloud. So yes, so we did know very early that, hey, we're affected in Google Cloud, and we need to start fixing things. Somebody could just go to Google Cloud and shut down machines at scale with a small script. It's not very difficult to exploit this. It really just looks like, it looks basically like this. Like, it's okay, you've got the exploit code. You would run it in your guest machine, shut down the physical machine, Google Cloud, other guest machines or host would basically shut down. It's pretty simple. You don't really know what other guests are going to be in that machine, but if you do this at scale, you could basically just spin up virtual machine, shut down, spin up, shut down. It could get really, really ugly. And now we're going to get to this. So a little bit of history. Back around 2003, the way that we used to manage applications running in our data centers was a little bit traditional, I would say, like kind of old style, where you would have a program that you run on a machine, and another team would have a program that would run on a machine. They would basically provision a machine and they'd run a machine, something like that. We have a lot of clusters around our data centers, but we weren't really efficiently using them. And the management of these systems was a lot of work. So what we wanted to do at Google was to find a way to automate the provisioning of these systems in a way that is very easy to manage globally at Google. And that was basically the birth of something called Borg. Anybody has heard of it? It's a cluster management system for Google data centers globally. So this is how we run software at Google, is like we use something called Borg. And then a couple of years later, from 2003, we wanted to run this at scale even more, basically by sharing resources. So to do that, you probably want to make sure that a resource is not going to be fighting with another process for resources. And that basically led to the development of C groups, control groups, which is kind of the foundation of how you're controlling access between resources on containers, right? Also, which was developed by Google. But then about 10 years later, something very similar to Borg came to the public domain. Anybody know what that is? Yeah, exactly. So this is how we got to Kubernetes, basically. Now, based on what I just told you, would you think this would be affected by the vulnerability? Probably, because we have machines, they share resources, they run on the same host, and some of them use Intel CPUs as well. So yes, we did have a lot of machines that run CPUs of Intel in cloud as well as on Borg infrastructure. And in Google, we still use Borg. We pretty much run everything on Borg at Google. Yeah. So this is what it is. It's basically a cluster management system for running our software across Google data centers globally. And so we were like, well, we've got Google Cloud, and we've got Borg. OK, and we have an embargo period of about a month. We have to basically find out a solution to this, fix it, and then at the end of the embargo period, we're going to have to be publishing this vulnerability to the public domain after we fix everything, so that other people can fix it. So what happened initially is go into Intel and basically report the vulnerability to them so that we can work with Intel on addressing this vulnerability. So that would be the initial step. And at the same time, there's like a circle of companies that include companies like Amazon, Microsoft, and Google, where we would basically work together on testing if there is a fix, and then collaborate, and then we address our vulnerability internally before it's published to the public domain. So you have to follow certain protocols very carefully. Is that all in terms of what could be affected? Can anybody tell me where else we might be affected? So I've been talking about servers. Do you think client devices will be affected? Do you have any clients running Intel? Yeah, and luckily we had Chrome OS, which was running Intel. So that was also, the Chrome OS laptops are also affected by this. So we also had to address the vulnerability there. But in client, like Chrome OS, it would basically just cause, like, you're halting the client. Like in a server, I know we talked about the shareability, and then you can shut down the host machine and affect other guests. But in clients, why would that be a problem? It's just an inconvenience, right? Unless you do what?
Unless you start manage to get the program to start every time you boot up.
Yeah, but first of all, how are you going to exploit a client in that way? So you've got your laptop, you've got a Chrome OS device. What would be like a scenario of an attacker that's actually going to use this vulnerability to cause you any sort of harm? Can you think of anything? OK. The answer is it's kind of right. Like based on what we've said so far, it is annoying. It could be annoying to basically try to cause your system shut down. But the thing is, it's a little bit difficult to exploit, but also it just shut down. And in clients, a little bit different than on servers, because on server, you're sharing services with other people, and then you can shut them down. It's a little bit different but things are going to change in a minute. So what happens is when we were doing the research at Google, Intel CPU in itself is a black box. We don't actually get to know all of the internals of it. So when we reported this to Intel, Intel did their own research, because they know the internals of the CPU. And they were like, oh, interesting. As it turns out, we can do prelude escalation through this. Now, when we're talking about clients, does that change anything? Now, it's a totally different thing, right? And it is possible, like in theory, it's possible that you could actually basically exploit the client system through a browsing session and call privilege escalation. Privilege escalation, basically, you could own the system, right? And I mean, back in the days when I was younger in the security industry, I was like thinking, you always want to attack servers. That's the big stuff. But now when you think about it, clients are very, very juicy targets, right? So, privilege escalation, nice. So what did we do here? We've got like, okay, we know we've got Google Cloud, we've got Borg, and we've got Chrome OS. These are affected. We're like in the first couple of weeks of this response, what are we going to do? First of all, we want to basically identify the machines that are affected. How many machines do we have, right? How many machines? And then once we get that number, how long is it going to take to roll out the fix? And we haven't even talked about the fix yet, right? But let's first start by counting the numbers. So we've got Google Cloud, and at Google, we've got pretty impressive systems in terms of like discovery. So you could basically just run like an SQL kind of query. Basically, it tells you these are the machines that are running Intel CPUs in Google Cloud or Borg or Chrome OS, for example. So we did that. We got all of these numbers. Now, the question is, how do we fix it? So there's like the option, of course, of like waiting for the vendor and hoping that they're going to fix it. But then there is this risk of what if it gets leaked, this vulnerability? Are we still just going to basically just wait on the vendor, be at the mercy of the vendor? And this is Google Cloud and Borg and pretty much everything. And then, or we could probably just come up with something on our own. So we did think about, okay, what can we do ourselves if the vendor doesn't give us something? And then somebody thought about an idea, which is this. So this particular engineer said we can use something like this. Can anybody tell me what she's trying to say here? For those who are familiar with CPUs and features enablement. Okay, that's okay. So turns out that sometimes in the CPU, when they have a new feature, they would give you a bit that you could flip on and off to disable a feature. And if you remember earlier, I said that the requirement for this vulnerability to be exploitable is it would be a system that uses that feature of FSRM. So you could disable that feature. So now you cannot exploit the vulnerability anymore. It's called the chicken bit. I think they called it the chicken bit because you can chicken out of it or something, something like that. So yeah, chicken bit. I think in the slide earlier, I showed this quickly and I went back, so you could have cheated. But anyway. So the next step is the microcode update. So Intel did actually indeed come back to us and say, we've got a microcode update that's going to fix this vulnerability without having to disable the feature. Now we've got two solutions. We've got the disabling of the feature and we've got the microcode update from Intel that we could apply. Now here's the question. Which do you think would be the better solution? And why? Can anybody tell me? Disabling the feature with a chicken bit, a firmware update from Intel that's going to fix it without disabling the feature. Which do you think would be the better option? Chicken bit. Yeah. Why?
Because then you don't need to trust Intel's code.
Let's assume we trust Intel code. Yeah.
Move away from the whole problem.
Yeah. So here's the thing. Earlier, when I was talking about FSRM, I did mention something important, that it was a performance feature. So when we disable it, do you think it might cause a problem? Yeah, so that was the issue. So basically, it would degrade the performance about 10%. So unfortunately, it's not as simple as going to Google Cloud customers and be like, hey guys, we're just going to go down 10% because we want to protect you from a vulnerable, like, right? It's like, yeah, like imagine I tell you, hey, I'm going to protect you against the DDoS attack by introducing a DDoS attack. Like, yeah, so that was the disadvantage. But that doesn't mean that it's a very bad solution, because what we did was keeping it in our back pocket just in case the vendor doesn't come back with something. And if we're in a situation where it gets leaked, or we come to a situation where we're like, okay, well, it's either we get hacked or we go down 10%. We might decide going down 10% at that particular situation, right? So we kept that solution in our back pocket just in case. But then Intel came up with the microcode update, and that fixed the vulnerability. So these are like the differences. The performance impact because of the chicken bit, and then the microcode update is effective, and also there's no performance impact. So the next step was microcode tested in PV. PV basically stands for production validated, which basically means Google, Amazon, and similar companies have tested microcode update, and now it qualifies as production validated. And this is a good solution we can rely on. The server microcode update rollout. So how are we going to roll out this particular fix? And there are a couple of strategies to do that. One way is to restart the machines, apply the firmware. Now again, there is an issue here, right? Like just rebooting machines for all Borg machines or like Google Cloud you might have to do it. And there are strategies you can do it, maybe like move the workloads to another machine and reboot this and then return back and things like that. It's a bit of a challenge. But then there's another strategy that we followed, where we basically applied all the microcode updates without rebooting the machines. And what we did was basically hot loading the microcode. So hot loading is basically just a mechanism by which you can apply the fix, you apply the firmware on the CPU without rebooting the machine, so it went transparently. So basically, customers or anything wouldn't be affected. Now, when I say transparently, technically, is it 100% transparent? Like if you go down to the cycles of the CPU, you're probably going to see a little bit of a difference. But it isn't something that would affect an application that runs on top of it. That's how we did it. We basically rolled it out like that. Now, when it comes to the Chrome OS fix, Chrome OS was a little bit easier because you get the fix, and then you would publish it to the clients, and they would basically download it and apply the fix. And that was it. So we didn't really have to worry too much about that. Now, I talked about a lot of things that we did. But do you think that all of this was done by 1, 2, 3 people? It's a lot of people. It's a team. And one of the things that we have at Google is something called IMAG, which is short for Incident Management at Google. It's a set of protocols and a process that we follow when we're managing incidents at Google. And everybody at Google follows these protocols when we have an incident. It's basically inspired by the same protocols followed by like medics and firefighters. Because it's kind of the same problem, right? You're kind of in a panic situation, and you want to follow a playbook without panicking, right? So this is what we have at Google IMAG. And in IMAG, at Google, once you start IMAG, in IMAG, once you initiate the process, you would start with building a structure of a team that's going to be managing this incident. And this structure would be different, would be separate from the management structure of the company or Google. Like, for example, in this particular case, I was leading this incident. I would be called the incident commander. I would basically be kind of like the CEO for that incident. I do remember when we did the training for IMAG at Google, they tell you this is the only time you can boss your own boss. Because if he helps in that incident, he would be the manager for that particular incident for everyone. So, but again, it's a responsibility, right? Like you're ultimately responsible for this. So in this case, I'm the incident commander. Of course, I wish the team was like this, like if we could just push buttons and like fix everything. Unfortunately, that's not the case. So this is what the team looks like. Initially, we start with something called the operations lead. This is basically the first person that I really need their help because they're going to start fixing things. What is the solution? How we're going to fix it? How we're going to roll it to all of the server fleet in an effective way. The operations lead would have like data center response lead that reports to him because that's going to be focusing on things like data center. And then, of course, Google Cloud lead, which is going to be under the data center. And these are only leads. These are not just the individuals of the team. Each lead would have a team that report to that particular lead. Everybody here is just a lead. And then we've got the Chrome OS also. There's a Chrome OS response lead, because there's going to be a lot of different challenges when it comes to client systems. So we have a lead in that area. And then we've got corporate response lead, and platform security lead. These are the ones that are going to be protecting like the internal corporate, internal systems at Google that are also affected by this. Tech research lead. This is the lead that leads the team of the research that identified the vulnerability. And then we've got the tech lead. The tech lead is really the highest level technical remediation lead within the response that basically leads all of the technical kind of elements. And he would lead the overall technical challenges, but also at the same time, they would engage with the vendor, like Intel. Now, communication lead. Unfortunately, for some people, that's, like you have to deal with things like communications. When you're doing this, for example, when you publish this to the public, you have to write something called the security bulletin. It has to be written in a certain way. So you'd have people that work in communication. It's not all just pushing code and writing code. And of course, for communications, we've got the internal communications. How are we going to tell the other Googlers that are Google there about this vulnerability and what they need to do? But then we're also talking about the people that are outside. And then the GCP support comms lead is the person that's going to be leading how we're going to communicate to GCP customers and deal with GCP issues, Google Cloud. Legal lead, because a lot of times these communications need to be approved from a legal perspective, so you need to have a legal lead. And then there is this interesting orange box. So, non-Google alphabets. Does anybody tell me what that means? If you're aware. So, there are alphabet companies that are not Google. And they also run systems. Like, for example, you've got things like Verily and some other companies that are also under YouTube, I believe, used to be like a non-Google alphabet company, and it came to Google. So you've got these other companies that are falling under alphabet but are not Google, but we also need to protect these companies. But the issue was, or the challenge was that we couldn't really fix the vulnerabilities at non-Google alphabet companies before the publishing of the vulnerability, because the NDA between Intel and Google was only with Google. So we had to plan things, but once it became public, we went to the other non-Google companies and told them, hey, can you fix everything just like everybody else in the public domain? So I had to rely on, appoint and rely on a lead for that particular part. So the last part of the response is disclosure. And this is a day when we basically kind of like celebrate, like, oh, we're done. It's disclosed to the public, and hopefully nothing bad is going to happen. So now when you in my opinion, one of the things that really scare me as a security engineer, and this is my opinion, my personal experience, aren't the actual professionals, like the security experts that work at big companies or the governments or like the sci-fi movies, like these people at these top, secret agencies or whatever. I don't think it works that way. It's actually the ones that have all of their time in their hands, and they're not doing this for money, and they're just doing it for fun, are the ones that are really scary. But when something gets published, I'm like, let's see what the world is going to bring us, because this is really the interesting part. That's in my experience. So when something gets published, I'm like, I think there is a good chance that somebody's going to find a way to exploit it in the client side. Somebody's going to find a way to exploit it much easier than we did. Or somebody might fork another vulnerability out of this or something, if you know what I mean. So this date came, and then we already had created the security bulletin, and we published it on the Google's documentation online and in Google Cloud website. And okay, we celebrated, it's done. We fixed everything by that date, and it's published, and now everybody else can fix it. And then one day, after this, after all of this, and we're done, and we're just about to go on holiday, we got this message from somebody from the public. So Cloud Shell is like this interactive shell environment in Google Cloud that anybody can use. So somebody said, well, look, guys, so just to give you a little bit of context, Icebreak tool is really the tool that we developed so that you can test your system and find out if it's vulnerable or not. So I should have said that earlier. Sorry about that. So somebody in the public domain sent us this message, said, okay, well, after all this, we actually tested this in Google Cloud in Cloud Shell, and it worked. So we were a little bit concerned. We're like, whoa, what the heck? Like, and then in a little bit of panic, we were like looking, okay, let's go to these systems. Are they really affected in Google Cloud, in Borg, or whatever? And let's do this quickly. And after a lot of analysis, here's what we figured out. Figured out that there was a bug in the Icebreak tool. So things were fine. But the Icebreak tool itself that was supposed to tell you you're vulnerable had an issue in it. So you couldn't trust it. So anyway, we fixed that, so it's fine. So that was good news. So I still could go on my holiday. So yeah. Ooh, yeah. It was a bit of a panic situation. It was kind of scary. So what did we learn from this? So some of the things that I think I really did learn from this is that when I followed this IMAC protocol, I was like really, really happy that I did, because a lot of the things, a lot of decisions we had to make and a lot of the work that we had to do was very important, and I really didn't want to get distracted by panic. I don't want to be like really nervous. I don't want to be very stressed out. I want to just follow a playbook and focus on the analytical important work. And the IMAC protocol really helped with that. And after that, I just kept telling my colleagues in the same team, do it this way. It's just going to make life a whole lot easier when you're dealing with a vulnerability like this. What can we do better? Well, I did lead that response. I don't think there's a way you can do it better. I'm just kidding. But actually, when I joined Google, like just a few months after I joined, I was complaining that, hey, I really want to work on something interesting. I want to work on something big. I want to get a vulnerability that's interesting and lead. And then one day, I kept complaining to my manager, and then one day they were like, there you go. So I was like in this situation, like, well, that's kind of maybe a little too big. So I was a little nervous, but at the same time, it was a really exciting experience that I actually went through. It's kind of like going to the army or something. Like after that, I felt like everything is just simple. So what can we do better? I think doing a little bit more exercises and basically becoming a little bit more comfortable with responses like this. There were some interesting challenges in between, like for example, in terms of communication and deploying things in our tooling that didn't work perfectly. And I think we could do better next time. They went well, but of course not perfectly, but again, like nothing is perfect. Can we automate? Of course, and this basically led to a project that I'm going to mention in a little bit that I worked on internally. Are we prepared for the next one? I do believe so. I think we have the strong processes and teams and tooling at Google to basically handle things like this properly if you don't panic and follow the MAC protocol and manage it properly. Now, so there's something called Google CPU Response Toolkit, which I developed after this response, which is basically a way to make responses to CPU vulnerabilities at Google more manageable. And as an incident commander, you wouldn't have to worry about creating artifacts, documentations, the fix readiness, the fix software and things like that might take a little bit of time, and it's really just manual work that you could automate. So what I did was developing a toolkit that you could initiate, and then a lot of this preparation work would be done. So you'd have things like artifacts ready, fixes ready, and then not the fix itself, but the pieces that would prepare the fix, and then communication with other teams, which teams do you need to involve, and things like that. And then you only focus on the important parts. So this particular toolkit is something that I developed, and then it was used subsequently for other responses, so that you don't have to do a lot of the things and just focus on other interesting things that are more analytical that involve you as an incident commander. That's it, and I really hope you enjoyed this and kind of got a little bit of an idea of how we do this kind of stuff at Google. If you'd like to connect with me, actually first, if you have any questions, feel free to ask me, but for reasons, I would suggest like ask me during lunch or outside. And if you want to connect with me after, it's pretty easy. That's my email. It's blackcat@google.com. And also, if you put my name on LinkedIn, we can connect on LinkedIn as well. Thank you.